Welcome to SCP-140's exploration of the solar system. We won't be looking at the very center of our solar system, which is the sun. That'll have to wait until later. But everything that orbits the sun is the subject of today's discussion. We'll think about the Earth as a planet and its moon. We'll think about the other planets that are closest to the sun in the inner solar system that are similar to the Earth: Mercury, Venus, and Mars. We'll also consider the large four outer planets: Jupiter, Saturn, Uranus, and Neptune, the moons of planets, also thinking about rings and comets and asteroids, and really many of the things that are in our own solar system. What makes these objects unique is that they have been visited by human-made machines and robots and probes that have sent back information. So we know a lot more about all of these objects than we do about the rest of what we'll be discussing in this class. Many of you are going to be doing a final project, which is a 5-minute presentation on a space mission. More than a few of those space missions have visited many of these objects. And so this is a great place to gain some context and understanding about what we know and what mysteries are still out there about the planets, the comets, the asteroids, and the moons that make up our solar system. So join me as we look at some of the amazing images and learn about some of the amazing observations and data that have been made about our solar system. We'll be searching through basically chapters 7 through 14, with the one exception that we won't be talking about the sun, chapter 9. That will wait until later. So this is the solar system. First, let's talk a little bit about how our solar system was formed. When we look out in space, we see lots and lots of places where material is collecting, generally coming together under the force of gravity. And as gravity pulls things together, the center of whatever the gravitational cloud is tends to get denser and denser, full of more and more things, more and more material. And eventually that's going to become the central star of a planetary system. So the upper two images you can see are artists' impressions of what a forming solar system might look like. However, you can also see some examples of observed forming solar systems below that. In the lower left are a number of places that have been observed throughout our galaxy where it is clear there is a central source that's turning on as a star with material swirling around it. As that material swirls around, it tends to collapse into a disk. The reason for that is because the disk is held out by the conservation of angular momentum. As objects are spinning around and spinning around, they can't lose that angular momentum. And so they end up flattening out in this disk, swirling around the sun. Eventually, that disk is going to fragment and form individual planets. And that's the story of the formation of our own planetary system. However, other planetary systems may form differently than ours. This is still an active area of research. At the bottom right, you can see some observations of dust around a star. And there are gaps in that dust, which many astronomers attribute to planets that are orbiting around in those gaps, actually opening it up through gravitational interactions. Keep in mind interaction like this, because we'll see other examples of this when we look at the rings around planets. In that middle image, you can see are actually a protoplanetary disk in its nascent form, just beginning to show up, darkening out the central star. And as that planetary disk begins to form, eventually that star will break through. The planets will be orbiting around the star. So here's the story of how planets end up forming in planetary systems. You can see the story 1 through 4 explained very much the same way that I was explaining. But the other thing that this explains are where many of the materials are going to be separated out in the disk that forms around a star. So you can see down below that the different materials that end up forming the different planets are due to the temperatures that they see at different points in the disk. At those different temperatures, different materials end up becoming solid. And then the materials that are not solid can get blown away into the outer parts of the solar system. So this explains to some extent what the composition of our solar system is. We also see a big gap in the sizes of planets in our solar system. The inner 4 planets are quite small, and then the outer planets are a little bit larger. And then what's interesting is that when we look at planetary systems beyond our own, there are a number of planets that are between the gap between the size of Earth and the size of Neptune. This is actually quite surprising to us. Our planetary system may be a little bit unusual. First of all, we have Jupiter that's pretty far away from the sun. Now, there are other planetary systems that have Jupiters far away from the sun, but many, many more have large planets that are closer to the sun, so-called hot Jupiters. We think we understand why that happens. Gravitational interactions will tend to cause large objects to go towards the center of a gravitational well. And so Jupiter, if it's formed, will tend to form very far out, and then through this process that's called dynamical friction, end up closer and closer into the center of the solar system, maybe even inside the orbit of something like a Mercury. Those are the so-called hot Jupiters, and they seem to be relatively common in our galaxy. In our solar system, Jupiter formed very far out beyond what they call the ice line, which is the temperature beyond which water turns to ice at about 300 or so Kelvin. And it sticks there. It didn't come into the inner solar system like other planetary systems. We're not exactly sure why that happened. Maybe there was less material in our solar system. Maybe there were other dynamical interactions which didn't allow for Jupiter to migrate in. Maybe the solar system is somehow more stable than others. But in any case, this is the solar system we live in. And one intriguing thought is, because here we are living on the 3rd planet from our sun, maybe that's what's required. Maybe a Jupiter not migrating in is what's required to stabilize a system so that we could have life on a planet. This is still a very open question. We've only discovered life on one world, our own. We continue to look for it in those other places, but so far, no luck. What are some of the other things that we can consider when we think about the formation of planets in a solar system? Well, the inner solar system, we have some planets here: Mercury, Mars, Venus, and Earth, ordered in size. And what you can see is that there are different things that occur over the course of a planet's life. The first thing that happens is the formation of the planet. They call that accretion. The accretion causes the planet to heat up, and then also will separate out the different materials. The densest materials fall to the center, and the lightest materials are on the outside. That's called differentiation. In small planets like Mercury, Mars, Venus, and Earth, a solid crust will form. And eventually there will be some volcanic activity. After a time, the volcanic activity stops, maybe slows down. Here on Earth, it continues. But on the rest of the terrestrial planets, there is no more activity in terms of volcanoes or plate tectonics. At that point, essentially, the entire world solidifies. And although some worlds still have very warm cores, that's residual heat from their formation, Mercury, Mars, and Venus, there are other worlds like our moon, which have completely cooled down and have no activity whatsoever. We also show here that this formation of a planet is somewhat dependent on the size of the planet. The smaller the world, the more pronounced the different features on that world will be. So for example, a world like Mars when it underwent volcanic activity, ended up forming gigantic mountains, much larger than those on Venus or Earth. And there is an example shown for you there where the largest volcano, which is now extinct on Mars, Olympus Mons, is shown to be at least twice or maybe 3 times taller than the tallest mountain here on Earth. So let's think about the Earth as a planet. As we said, the Earth has a hot core, molten in fact. That drives a lot of the activity on our planet. The reason we have mountains and earthquakes and different kinds of crust is because there is roiling and boiling and motion that's happening in the interior of our world. Our world also has a magnetic field that protects it from the solar wind. These are very highly energetic particles that would strip our planet of our atmosphere and be quite dangerous to life, except that we're protected by this magnetic field. This also is what causes the aurora, the northern and southern lights, these charged particles spiraling down our magnetic field towards the poles and interacting with the atmosphere up in the polar regions of our planet, either in the North Pole or the South Pole. So this is one of the things that makes our world unique, its magnetic field, and the other thing is its volcanism. Of course, other things that make the world unique are the fact that there are moving plates in the crust. Other solid crust planets don't have these moving plates. And here are some examples of those moving plates on our own planet and the results of them. In the lower left, we see a fault. It's called the San Andreas Fault, which is a place where 2 plates are either coming together or stripping apart. And in the upper right, we see mountain building. This is mountain building in South America, where we get some very, very tall mountains where 2 plates come together and push up mountains, forming either volcanoes or what we call fold mountains. Earth's atmosphere is also very unique. You can see a diagram that explains Earth's atmosphere at the bottom. The temperature at first, as you go up in our atmosphere, starts to drop. But then when you hit about 20 or so kilometers up, it begins to get hotter again, quite surprisingly. It's only after you pass the ozone layer that the temperature again starts to get colder until you get to the highest ranges away from the planet. And the temperatures of the gases, which are very, very rarefied at that point, are very high. If you were at those altitudes, however, it would seem very cold to you because there's so little gas in that part of our atmosphere that you wouldn't be able to be warmed by conduction, which is the main way you're warmed here on our own surface. So you can use this diagram of Earth's atmosphere as a way to compare to other planets we'll be looking at. Earth has a very dynamic atmosphere. There are obviously very strong storms that can form, as you can see here. We have clouds that form and also a very complicated interaction with sunlight as it hits the planet and gets absorbed by different materials in our world. You've already done a laboratory investigation looking at the greenhouse effect, which keeps the Earth a little bit warmer than it otherwise would be, which is good because this allows for liquid water to be on the surface. However, human beings have been adding more and more carbon dioxide from ancient stores of it beneath the crust to our atmosphere over the last few hundred years. You can actually see a graph of how much carbon dioxide has been increasing in the lower left. This is directly related to increasing average temperatures in our planet, which will completely change the climatic system that we're used to. The Earth is going to be fine. It might get very, very hot. Life will probably survive, but who's going to suffer will be humanity. This is what we're concerned about when we talk about climate change. Of course, volcanoes are also involved in the interactions in our world. Volcanoes can move a lot of carbon dioxide into our atmosphere just as much as burning fossil fuels can. We happen to be in an era where there's not as much volcanic activity as there was in the past. And in some ways, the factories and the cars that we're producing are acting like their own volcanoes, bringing up all that carbon and releasing it into the atmosphere. The other thing that can happen with interactions between the Earth and space are collisions. large objects are swirling around our solar system even still, although in the past there were far more of them. And when they crash into the Earth, they form these craters, which you see at least 2 examples of at the top. In fact, when really large meteors crash into the Earth today, they can cause tremendous damage. There's a picture in the upper right of trees that were felled by a meteor, which is some space debris crashing through our own atmosphere into our planet. We see evidence of these happening all the time. In the lower right, you can see a shooting star or a bolide. These are pieces of evidence that there is material coming in from space burning up in our atmosphere. That's exactly what shooting stars are. Of course, famously in the lower right, there was a gigantic collision that occurred about 65 million years ago in the Yucatan Peninsula of Mexico. This was implicated directly in the extinction of the dinosaurs. So these giant impacts can have some influence on our own planet. All right, let's move off of our planet towards our moon. You can see lots of amazing views of the moon, the only other world that we have visited as human beings. There's even a picture of a human being looking at a rather large rock in the second picture from the upper right, and a footprint in the upper right. You can also see different parts of the moon. There are the darker areas they call the mare, or the seas. Those are ancient lava beds. And then there are the lighter areas, the highlands, which include mountain ranges and also lots and lots of craters. Those craters are made by the same processes that make craters on Earth, in particular, the collisions with objects that are flying through space. Meteoroids is what we normally call them. How do we know these are made by meteoroids and not volcanoes? Well, we'll get a good look at that. But one thing to notice is that there's a big difference between the highlands, which you see where all the craters and the mountains are, and the seas, which appear very flat, not very many craters at all. This is because those seas of ancient lava beds have erased all of that old activity and all of the old terrain, and basically made it smooth, and then no further cratering happened afterwards. At the center of some large craters, you can even see seas forming. This is places where a crater was formed by a collision, and that collision was strong enough to cause some melt of the rock and a sea of lava to form. That's in the lower right-hand corner. So how do we know that these craters are caused by volcanoes, or not by volcanoes, but rather by impacts? Well, the craters that are formed by impacts look different than volcanoes. You can see the different shapes that they have in this image here, and also how these craters end up forming. We can actually use the number of craters we see to decide how old a terrain is. The more craters, the longer it's been that way. There was a time about 4 billion years ago when cratering was really, really common. Impacts happened all the time. It's died off considerably since then, although there are some recent craters on the moon, including one that you see in the lower right. We're going to move to another cratered world that looks very similar to the moon, similar enough that many students mistake it for the moon. This is the planet Mercury. Mercury is a little hard to observe from our own planet, but we've sent a few space probes there and mapped it. You can see a false color mapping of Mercury in terms of the highest and lowest reflectivity of radio waves. That's in the lower left. We've worked out the interior of Mercury is a hot core. It still has some residual heat, but there's no more seismic activity. The planet itself has kind of collapsed down. It's shrunk, and in that process has created some rather large cracks, including one you can see in the lower right. Of course, there's lots and lots of craters on this world. This is because there isn't a lot of activity to erase those craters. Mercury is also one of the first planets that we were able to measure its rotation rate very accurately. We did this by bouncing radio beams off of it. There is an explanation of how that works in the middle of this slide. Let's move on to the sister planet of Earth, Venus. Venus is an extremely hot world. Mercury is quite hot during the day, but at night it gets rather cold because it has no atmosphere. But Venus has a very thick atmosphere, and consequently, the greenhouse effect has run away. Temperatures are routinely above 900 degrees there. Because of this, there isn't much to speak of in terms of possibilities for missions to land on Venus. There were some that landed in the 1960s and 70s, and there's one picture we have of the surface down at the bottom. But since then, we haven't landed many landers on Venus. The conditions are just so hot. We do see evidence in the past if we bounce radar waves off of the surface, because we have this clouded layer that is preventing us from seeing Venus's surface with our optical instruments. But we can still see old volcanoes and craters that show up on the surface, and some areas where that shrinking planet similar to Mercury has been seen. Venus doesn't have a magnetic field, or whatever magnetic field it has is very weak. And it also is not seismically active. There are no more volcanoes than there were in the past. We'll move past Earth to the next planet in the terrestrial zone of our solar system, Mars. Mars is the most visited planet in our solar system. Here are some pictures of the various spacecraft that have landed and driven around Mars, showing some really interesting things. And we have an interesting view of Mars, including the ice caps that are at the North and South poles. All kinds of interesting things seem to be showing up on Mars. There are craters like you see in the upper right and the upper left. We have landslides that are showing windstorms. The largest volcano and the largest canyon in the solar system are both on Mars. Mars has some very unique features on it, including some of the highest mountains and some of the lowest depressions. One of the biggest craters in our solar system is seen in the purple region, that false color region of Mars on the lower left. Mars also has some interesting weather patterns, including ice. Some of the ice is carbon dioxide ice, but others have been shown to be water. In fact, the evidence that there is water ice is seen in the lower right, which is two pictures that were taken one after the other, where the ice seems to be disappearing. And that's happening because it's water ice. Water ice on Mars disappears much more quickly. It sublimates is the word for it, much more quickly than carbon dioxide ice. And this is the detection of water ice on Mars by the Phoenix lander. We also see lots of other pieces of evidence for wind erosion, things that are moving around, dust devils, and also ice layers at the ice caps of Mars. Mars used to have water flowing on the surface, or at least we have strong evidence that that was the case. There are places where we see rocks that look very similar to the rocks on Earth, which are formed at the bottom of riverbeds or lake beds, often at the bottom of craters. We can also see places where rivers seem to have flown once, although there's no water flowing on Mars now. There have been some intriguing pictures at the bottom of places where some dark streaks show up and disappear, which have led some people to think that there's evidence for water flowing underground and very, very near the surface, or maybe even on the surface from time to time. Mars has a very thin atmosphere, and so it's only a small chance that you're going to get any liquid water on the surface of Mars. In the past, Mars's atmosphere was much thicker, and we think that in the past it probably had oceans and lakes and rivers similar to Earth. Could there have been life on Mars in that time? Well, there's a strong possibility if the climate was similar to that of Earth's. We're still searching for evidence of that. We haven't really found any. In fact, some people think that some life may still survive on Mars, and that's being searched for as well. All right, let's move to the 4 planets in the outer solar system. These are planets that are made mostly of gas and ice. You can see their compositions down there on the bottom and what those planets look like at the top on the left. These planets all have very high wind speeds across the planet because they're spinning around very, very fast. And if you want to see what their atmospheres are doing, you can see they have different cloud layers, which actually account for the different colors that you can see on the different planets. Jupiter and Saturn have the lighter colors because they're dominated by ammonia clouds and also ammonium sulfide clouds. And then Uranus and Neptune are bluer in color because they're dominated by some methane clouds, which tend to look blue. And perhaps there's some hydrogen sulfide clouds beneath them. Let's first consider Jupiter and Saturn together here. On the left here, we'll look at Jupiter. Jupiter has some interesting features. It's the largest planet in our solar system. It has this giant storm called the Great Red Spot, which has been around for hundreds of years. It's about 3 times the size of Earth. And in the middle of the top, you can actually see what Jupiter looks like if you look at it with a radio telescope. It's got these 2 bright spots swirling around it. This is due to material that is in orbit around Jupiter that's at very high temperatures. It's actually ionized as a plasma. It's called a plasma torus. So Jupiter has a very violent interaction around it as a planet. You can see some of the pictures that have been taken by Jupiter at the bottom above letter B. This is a picture taken recently by the spacecraft Juno. And we've also sent a probe into the atmosphere of Jupiter. This is an artist's conception above letter A by the Galileo space probe, just to test and see what those cloud layers were made out of. To the right, we're looking at Saturn and Uranus. Saturn has rings that surround it sort of famously, and you can actually see Earth in that picture, taken with the Cassini spacecraft. Uranus also has rings, and what's interesting is that Uranus is tilted on its axis about 90 degrees, and the rings are moving around the planet in the same orientation that the moons are moving around in the same orientation that the planet is rotating. Something must have hit Uranus early on to cause it to tilt onto its side like this. It's still a little bit of a mystery as to how this happened, but it makes for a very interesting planetary system. All right, we're going to move out to looking at the objects that are orbiting around some of these outer worlds in our own world. These are the moons. And then we'll also be looking at the asteroids that don't orbit any particular planet, but are actually orbiting in belts around the sun. The main belt is in white, you can see on the right. The Trojan belts follow Jupiter, the Greeks lead Jupiter. And then there's another group of asteroids called the Hildas, which are between Jupiter and the main asteroid belt. We'll start off with the moons of Jupiter. So I said that Jupiter has a plasma torus around it. Well, that's caused by one of its moons. It's the most seismically active world in our solar system. The moon is called Io. You can see pictures of it here, including some diagrams that show that there were active eruptions on the surface of the world. And you can even see some lava on the surface in the lower left. An amazing world with plumes of material that shoot so high over the moon that they actually escape the gravitational pull. That forms that plasma torus around Jupiter. The other 3 large moons around Jupiter that make up the 4 moons we call the Galilean moons are known as Europa, Ganymede, and Callisto. And these are all ice worlds. They have surfaces that are predominantly ice, and each of them, we believe, has a subsurface ocean. The largest subsurface ocean may belong to Europa. Now, this is sometimes confusing to students. How is it that Mercury, for example, has basically stopped all of its seismic activity? And here we have worlds that have warmed up, that are tiny little moons in comparison, but have enough heat to have an ocean that surrounds the entire world, at least under the surface, and Io, which has volcanic activity. Well, the reason for this is because there are interactions gravitationally between Jupiter and these moons, which tend to warm them up. These are the same interactions that cause the tides here on Earth. We call them tidal interactions. These are interactions that cause a stretching of moons back and forth. And as that stretching happens, it heats up the interior. And that's what allows us to have these strange systems. The fact that there's a giant ocean beneath the crust of Europa makes us wonder whether there could be life underneath that crust. There's an entire world of water. In fact, more water on the moon of Europa than there is in all the oceans of our planet. Could there be life forms there? Maybe, but it's going to be very hard to check because we have to get through kilometers and kilometers of ice to really see what's going on in that ocean. There's another interesting moon out there, a moon of Saturn called Titan, which has a very thick atmosphere. It's the only moon that has such a thing. You can see a diagram of that atmosphere on the lower right. But what was interesting was when the Titan was discovered, we couldn't really see the surface because that atmosphere was too hazy. It's only been recently with new improved infrared sensors and also a probe that landed on the surface and took the picture you see in the upper right, just to the left of the view as you come in through the atmosphere and land on the surface of Titan, that we've really gotten our view of the surface of this world. And what's amazing is that there are lakes and there are rivers. There seems to be flowing liquid on the surface, but it's not water. It's methane or ethane. These are organic chemicals that we would normally see as gases here on Earth. But under the cold and high pressure system that we see on Titan, they actually form a liquid, and they have a raining cycle. They have a cycle where the rain falls, it forms into liquids, and then it evaporates, just like we have the water cycle here on Earth, except it's with these weird chemicals. This moon is intriguing enough that there's active proposals to go visit it again, including one to visit in the next 10 or 20 years, where they're going to hopefully fly around in this very thick atmosphere, because flight would be very easy since there is less gravity, less surface gravity on Titan in a very thick atmosphere. On the upper left of this slide, you're seeing some pictures of one of the moons of Neptune that we believe was captured from the outer solar system in a place called the Kuiper Belt. This moon of Neptune is called Triton, and it is also undergoing quite a bit of seismic activity, except you're so cold all the way out there at the edge of the solar system near Neptune that the seismic activity turns into geysers of liquid nitrogen. Some of the coldest stuff you can imagine. But those geysers have resurfaced the entire ice world. And that's what you see there in the upper part of this slide. Not to be outdone, we've also visited a world which we no longer consider a planet, that's Pluto, and have taken pictures of it. The picture in the lower right is perhaps the most famous view of Pluto that has the ice field that has really formed. As Pluto goes in its orbit, it comes closer or farther from the sun. When it's closer to the sun, it has an atmosphere, and as it gets further away, that atmosphere tends to freeze out and fall to the planet, forming these giant ice fields. Pluto also has a moon in the lower left called Charon, which has some very interesting features that are seen in it. It looks very similar to Pluto, but has also undergone some similar scenarios where there have been events which have erased some of the surface, making the surface newer with kind of an ice sheet surrounding it. We'll think a little bit, and you can read about rings of various outer worlds. The 4 gas giants all have rings that surround them. These are places of gravitational instability where moons can't really form. And so instead of a moon forming, we have material that's surrounding the world. This dynamic material, in fact, isn't very stable. It only survives for some short amount of time before ending up colliding with the planet. And the rings of Saturn may not be there forever. But we have lots of really interesting evidence for what's going on in the rings of Saturn. We see that there are tiny moons that are shepherding some of these rings and causing different waves to form in them. That's seen in the lower left. And there's an outer ring of Saturn that's formed by material that is being replenished by one of Saturn's moons, Enceladus. Enceladus also has a subsurface ocean, kept warm by tidal effects, very similar to the subsurface oceans of the outer three Galilean moons of Jupiter. But here we have geysers that are spewing out. Now, the Galilean moons of Jupiter also have geysers, but they're not nearly as dramatic as Enceladus's geysers. And those Enceladus geysers are strong enough so that the material escapes from the world's gravitational pull and forms a new ring around Saturn, providing some of the material to replenish the ring system. You can see an artist's impression of what the system of rings actually looks like close up. People often think that the rings of Saturn would be solid rings going all the way around, but they're not. They're made out of tiny little particles. Some of them are as small as a grain of sand. The largest ones probably get up to about the size of a house. What about some of the other things in our solar system? Comets and asteroids. Well, at the top, you'll see a comet. This is Comet Hale-Bopp. Comets are things that come from very, very far out in the solar system and swing in on we call them eccentric orbits. Sometimes those orbits are eccentric enough that they don't ever really come back. Or if they do have orbital periods, they're of thousands of years. So when you see a comet and it springs around the sun, you might never see it again in your lifetime. Other comets just have very long periods, like Halley's Comet. Famously has a 76-year period. In fact, you can see what the Halley's Comet actually looks like in the lower right. That's the nucleus of the comet, where the main material is. And the stuff that's spewing out is basically coming out because the comet's getting warmed up as it gets closer and closer to the sun. And the volatile materials are exploding out in jets. So comets come into our inner solar system and look amazing because all of this material is coming out and the tails are streaming back, always facing away from the sun. So that's an interesting feature that comets have. But some comets end up interacting with all of the gravity in the solar system, end up colliding with other objects. Famously, there was a comet that collided with Jupiter in the 90s, and there's a picture of what happened when that occurred. That wound you see on Jupiter no longer is there. But if you were to superimpose the Earth, it would actually have decimated the entire planet if it happened to us. It's interesting to think that Jupiter might be protecting us from such collisions. At the lower left, you can see some other objects that are in our solar system, the asteroids, which I was talking about earlier. The very bottom, the two biggest asteroids in our solar system, Ceres and Vesta, are seen. They're big enough to have their own gravity, so they become rather round, but most asteroids are not large enough to be able to form that round shape under their own self-gravity. They end up becoming rubble piles, and they look a little bit more strange shaped, like you see in the lower left. So that's what I wanted to talk about for our exploration of the solar system. There's a whole lot more for you to learn about, but I think that this is a good start. This is a good introduction. Please read through the chapters. Think about the questions that are being asked in the problem sets as you go through them. Try to answer them to the best of your ability and check out those different chapters and resources that we've put here so that you can learn more about our amazing solar system. Once you know which objects you're most interested in, and after you write some of the discussion board posts that we've requested of you about some of the objects in the solar system, you might think carefully about whether the project that you've chosen for your final project is a good one, in the sense of it being interesting for you. Most of you are going to choose one about a space mission to one of the worlds that we were looking at, or one of the phenomena. And if you're interested in those, make sure the space mission that you chose can directly talk about that. It would be a nice thing to include. So thanks very much. Enjoy your exploration of the solar system. The next time you hear from me about the universe, we'll be talking about stars.